lovely to be here again. And I was thinking maybe it's time for some more organic chemistry. I feel like I haven't talked about organic chemistry in a little while. And since the last video I recorded was on inorganic transition metal chemistry, maybe a little organic would be good to do today. So I decided carboxylic acids are what we're gonna do. So I created with my molecular model kit a carboxylic acid, a specific one we'll talk about later. But we'll start out with a little bit of drawing structures and talking about carboxylic acids with my trusty Twisby fountain pens that, if you know me and if you've watched my videos, you know how much I love these things. They're just truly the best. My earliest YouTube videos I started making almost 4 years ago. I used the old style nibs where you dip in the pen into the ink, and that was really fun to do. But I've moved on, you might say, to these different kinds of fountain pens that I really like. And I think I started out with just one, and then eventually I got some of different sizes, and so I could have different colors handy. So I love my pens, as you can tell. So let's talk a little bit about carboxylic acids, shall we? Move my pens over a little bit, give us some room here. Alright, so carboxylic acids. As is true for any of the functional groups in organic chemistry, we can write them out generically, where we can say that there is what we call an R group. That's could be anything. It could be a hydrogen. It could be some more carbon-based structures. So a common way to write out carboxylic acids is to write it out like so. This can be confusing for general chemistry students, for students who haven't learned a lot about organic chemistry, because it might be tempting to interpret this as carbon directly bonded to oxygen, which is then directly bonded to another oxygen, and then hydrogen. This would actually be a peroxide if it was bonded in that way. So I wanted to clarify what this really means when you write it out in this COOH way. So structurally what it means. And again, the R can be anything. So we're just going to focus on what's going on here with hydrogen, here, oxygen, carbon, and how they're bonded. Okay. So what this is saying is that we actually have this carbon is double bonded to an oxygen. Okay. Now we could have drawn the double bond this way, but I didn't feel like I had enough room, okay? It's just fine to put it in either direction, okay? And then this carbon is then bonded to the other oxygen. So notice how this carbon is bonded to both, and they are not bonded together. And then this oxygen is bonded to the hydrogen. This oxygen does have 2 lone pairs, as does this one. But sometimes in organic chemistry, those lone pairs are not included. They are just assumed to be there. So don't be surprised if you don't see them. Okay. One other thing to point out is that these bond angles are not 90 degrees, as you might think when you look at them like this. And this is not linear. Alright, so that means we need to invoke Vesper theory. Alright, Vesper theory. Valence shell electron pair repulsion theory. That gives us information about structures and bond angles. So why don't we take this a little bit further and draw this out where we are a little bit more specific and accurate with regard to these bond angles. Okay. So why don't we first consider what is the hybridization of each one of these, this carbon and the oxygen there, and that might help us when we are considering these bond angles. Okay. So this carbon, we're not going to worry about the R group because we don't know what that is. It's just generic, okay? This carbon here, it's got 3 of these single bonds. Over here there's a double bond as well. So these are sigma, 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 and then the other one is a pi bond. So here we have a sigma and a pi bond. And when that's the case, that means that you have an sp2 hybridized element. Okay, so this carbon is sp2 hybridized. This oxygen here, let's take a look at that. It's got a lone pair, sigma bond, pi bond. And in that situation, it is also sp2. Okay, let's take a look at this oxygen here. We have a sigma bond, 2 lone pairs. When that's the case, it is sp3 hybridized. Okay. So now knowing the hybridization, and if we recall those, and keep in mind this video that I'm making, I'm not teaching specifically about hybridization and valence bond theory. Alright, so this is something you can go back and review. You can look at other videos I've made. And I'm thinking maybe I'll make another video talking about hybridization. But in any case, when this is the case, we get 120 degrees around this central atom, okay? So these three bonds, they are going to configure themselves 120 degrees from each other based on Vesper theory. This oxygen here, sp3 hybridized, so this bond angle is going to be 109.5 degrees. So let's redraw this structure here that depicts the bond angles a little bit more accurately. Okay. So let's look at this. Okay. Alright. Give myself a little bit of room here. So here's our R group. And this I will have bonded to this carbon. Okay. Now remember, we need 120 degrees around this carbon. So that means that one of these oxygens will be up here. I'll make this this oxygen here. I'm going to wait to fill out the lone pairs. You'll see why in a minute. Okay. And this one, I'll make this the double bond to this oxygen. Okay. So what we have here, maybe I'll get my red ink pen. We have 120 degrees all the way around. Now, admittedly, I did not draw these perfectly, but I did okay. Okay. Are they exactly 120? Not necessarily, right? Because perhaps this R group is a very large, bulky group, and sterically it might cause these to be squeezed a little bit this way, but it's going to be close, okay? So you can assume these are all close to 120 degrees. Okay. Now let's look at this oxygen here. It's got two lone pairs, and it's got this other bond to the hydrogen. It's sp3 hybridized, so that means it is going to be 109.5. And so what I can do here is draw the bond to the hydrogen. And this bond angle here, I'll make this one blue maybe, see a little bit better. Oh, where's my blue? Here we go. Okay. Right in here. This is, oh gosh, where am I gonna put it? Oh my gosh. What a conundrum, right? 109.5 degrees. Okay, so there's our 109.5 for sp3 hybridized oxygen. Alright. Let's bring my model kit over so you can see what we're looking at here. Okay. So notice here's our, so over here is the R group. aside, and we'll talk about that when I show you exactly which carboxylic acid this is. But here's our double bond, carbon double bonded to oxygen there. Okay. And then here's our single bond to this other oxygen, that one. So notice how this bond can actually rotate, okay, because it's a single bond. So this hydrogen, I could have drawn it up there, right, because it can actually spin around. So sometimes you arbitrarily choose which direction it's going to go. Alright. This bond, however, cannot spin around because it is held in place. We have a single bond and a pi bond. With this model kit, you don't really see that sigma bond. Here you just see the pi interaction, electron density above and below the plane, or the bonding axis. Okay. This whole thing here, here's our carboxylic acid group. Okay. So, depending on what R is, we have lots of possibilities for what the carboxylic acid might be. Okay. And so, I wanted to give a couple examples. And one of them is what I made here for you. Okay. So let's draw it out first, and then we can talk about how this model is showing us the structure. Okay. And this particular carboxylic acid is lactic acid. So this is what you get when perhaps you exercise too heavily and your cells go into anaerobic respiration, and there can be a buildup of lactic acid. So those of you who've had some biology or biochemistry, I'm sure you've seen this before of how the lactic acid is formed. So right now we're not going to go into the details of that, but rather we're going to look at the structure of lactic acid. Okay, so there's a couple ways we can draw this structure, and one of them is showing all the atoms. I'll do that first, where we have our R group here. And you'll see why it's a little bit tedious drawing out all the atoms when we are drawing out the structure. So this is more of a Lewis dot kind of structure. Okay, where this whole part here is the R group. So why don't I use a different color to show the carboxylic acid part of this molecule. Alright, so here's our carbon that's double bonded to the oxygen and single bonded to this OH group. I'll put the lone pairs in here. Okay. So here you can see there's our carboxylic acid. Okay. By the way, it's called an acid because this hydrogen is called the acidic hydrogen. This bond is fairly weak, which allows the hydrogen to break this bond here with that oxygen. This is due to something called the inductive effect, where we have a very this bond weakening a little bit. So this hydrogen can be released much more easily than, for example, this hydrogen on this alcohol group, or this hydrogen that's directly bonded to carbon. These are not very acidic, but carboxylic acid groups, indeed, this hydrogen can be released. It is not a strong acid, though. Okay, so a small percentage of the hydrogen is released in these acids. Okay, so here's lactic acid drawn out in this way, but I did want to draw it out with line angle drawings, and then also show you the structure that I built with the three-dimensional model kit. So, if we're drawing this out with line angle drawings, okay, line angle drawings, the carbons are inferred wherever you have a vertex like this. There's our double bond to our oxygen. So we are showing the heteroatoms. We often don't show the bond between oxygen and hydrogen, so we see it like that. Okay, so there's that oxygen, there's that one. It's also common to leave off lone pairs. And so this carbon is then bonded to this carbon, so there's that carbon. And this one goes up to be bonded to this one. And here is the alcohol group that is coming off of this carbon right there. Alright, so this is lactic acid that is drawn with line angle drawings. Much easier, isn't it? Indeed. And now let's bring in the three-dimensional structure. Okay. So here is the methyl group. This is this last carbon there. Or if I show this one, it's this last carbon there. Right. That's what's here. Okay. This carbon is the one that has the alcohol group on it. So why don't I turn these, since these are single bonds, they can rotate around. So this can rotate like that, right? Okay. This carbon has a hydrogen bonded to it as well. There's our oxygen and hydrogen for the alcohol group. Okay. 109.5, 109.5. All these are 109.5. Okay. And then here's our carbon double bonded to the oxygen. Okay, so that's corresponding to that part. And here's our single bond to this oxygen with hydrogen. So this is our acidic hydrogen right there. Okay. So it's very helpful to create molecular models where you can really see the bond angles, and you can visualize a lot better when it is possible to rotate around different bonds that's a little bit about them. And I hope you found this gentle, soothing, and educational. I really hope you enjoyed it. And I also encourage you to let me know if you do have requests, or if there's anything else I can teach you or show you or talk about on this channel. I'm always happy to be here for you. That's why I love doing this channel. So, ASMR Chemistry. Please like and subscribe if you have enjoyed it and you'd like